Last video on standing waves is going to talk about the math of standing waves. You knew there had to be math here somewhere. So, obviously the first harmonic pattern, we can see what's going on here. Wave starts here and finishes here, right? One crest, one trough, one wavelength. One complete wave consists of two loops. Then each loop is equal to 1/2 wavelength. And you can read through this. But here's my point, okay? With the first harmonic, right? First harmonic is where you have this. You have the one antinode and two nodes. The length of our rope, or our length of our tube here, from where it's made to where it finishes, is equal to 1/2 of the wavelength. So let's look at the second harmonic pattern. We have here 2 over 2. So our length is equal to our wavelength. Here we have 3. 3 antinodes divided by 2 times the wavelength equals the length of our string, or the length of our area here between our waves. So the nth harmonic is L to the N over 2. Okay. When we look at N, right, N is just going to be our antinodes. So as long as we know the number of antinodes and the wavelength, we can find the length or so forth, right? So that's our equation. We have to know antinodes. So let's look at some problems here. Suppose we have a string that's 1.2 meters long and vibrates in the first, second, and third harmonic standing wave patterns. Determine the wavelength of waves of each of the three patterns, okay? So the first, second, and third harmonic. Now remember, that's the number of what? When we talk about harmonics, think about it. Number of harmonics is going to be the number of antinodes, right? So we just think about the number of antinodes in our harmonic. So if we have the first harmonic, it's going to be n over 2 times wavelength. Our length is 1.2. For the first harmonic, it's going to be 1/2 wavelength. And if we do the math, we divide both sides by 1/2, we get wavelength of 2.4 meters for our first harmonic. Our second harmonic, 2 over 2 here. So our length is 1.2. That's going to be equal to our wavelength. So 1.2 meters is our second harmonic. There's a thing there. Our second harmonic, the length is going to be the same as the wavelength, because it's a single wave. 2 loops would be a single wave. And now a third harmonic would be here. 1.2 is equal to 3/2 wavelength. Okay, we're going to divide by 3/2 or multiply by 2/3, however you want to do that. But we get 0.8 meters as our wavelength. So as we increase harmonics, our wavelength gets smaller. Alright, so now we got a string here at the right, and the string at the right is 1.5 meters long and is vibrating as the first harmonic. The string vibrates up and down for 33 complete cycles in 10 seconds. We want the frequency, period, wavelength, and speed for this wave. So we just go back to everything that we know before, okay? We know our length is 1.5 meters, okay? And it's vibrating in the first harmonic. So first thing we can do is we can find our wavelength, right? And we can, our length is 1.5 meters long, 1/2. So we just multiply both sides by 2, so our wavelength is going to be 3 meters. So we know our wavelength. Now we want to find our frequency. Our frequency, we get 33 cycles in 10 seconds. So we get 33 cycles in 10 seconds. So our frequency is 3.3 hertz. To find our period, obviously we take 1 over 3.3, and we get 0.303 seconds. So that's our period. So period, frequency, wavelength, and then speed, remember, is just frequency times wavelength. So we take our wavelength of 3, multiply by 3.3 for our frequency, and our speed is 9 9.9 meters per second. And so the speed of our wave is 9.9 meters per second. So we can use harmonics to do all the same math that we've done before. Okay, let's look at another one, just to be sure we're good. String at the right is 6 meters long, and it's vibrating as the third harmonic. How we know it's third? Because we have 1, 2, 3 antinodes. It vibrates up and down with 45 complete cycles in 10 seconds. Determine the frequency, period, wavelength, and speed for this wave. Same steps, okay? So my wavelength, L, is equal to n over 2 times the wavelength. We're in the third harmonic, so our length is 6 meters. We go 3/2 wavelength, take 6, and we divide it by 2/3. Or multiply it by 2/3, divide it by 3/2, and our wavelength is going to be about 4 meters. So our wavelength's 4 meters. Frequency is 45 divided by 10, or 4.5 hertz. We take the inverse of our frequency, so this is our frequency. We take the inverse of our frequency, and that's our period. It'd be 0.222 seconds. So that's our period, and then speed. It's going to be 4 multiplied by 4.5. So 16 and 2, 18 meters per second is the speed of our wave. If you have any questions about these, please see me, but I think hopefully it'll start making sense to you what's going on. But just to be sure, let's do one more. The string at the right is 5 meters long and vibrating as the fourth harmonic, okay? Fourth harmonic, because we have 1, 2, 3, 4 antinodes. Vibrates up and down with 48 complete cycles in 20 seconds, frequency, period, wavelength, and speed. Let's do a different order. Let's find our frequency first. Frequency would be 48 divided by 20. So when I take 48 divided by 20, I get a frequency of 2.4 hertz. If I take 1 over 2.4, that'll be my period of 0.417 seconds. So we have our period. So there's our period, there's our frequency. Wavelength, we know the length of our string is 5. We're in the fourth harmonic, so it's 4/2 times wavelength. So it'd be 5 divided by 2. So wavelength will be 2.5 meters. Since our speed is wavelength times frequency, 2.5 times 2.4, we get approximately 6 meters per second for our speed.